All right, so today we're going to take a look at a topic in Chapter 5. This whole chapter deals with rational functions, and you can see there with our objectives, we're going to first determine the domain of a rational function. Rational, just think of the word fraction. These are functions that are in fraction form. We're going to be able to identify vertical asymptotes if they exist, because that's helpful when we start graphing these in just a lesson or two. And then how do we find horizontal or oblique asymptotes? That's a new topic that you did not get in Algebra 2. So let's just jump right in. How do we find the domain of a function, a rational function? Well, we have to be careful when it comes to domain. Another word for domain is input. So by looking at what the domain is, it's like saying, what are the numbers that are allowed to be inputs? And so the focus really becomes the denominator, because we always have to be aware of not creating 0 in the denominator. It's not possible to divide by 0. So when it comes to inputs, we have to make sure we don't input numbers for x that create 0 in the denominator. So this one's probably pretty obvious to you, but anytime you want to find the domain of a function, you can literally just take the denominator, make it equal to 0, and solve for x. And what that will tell you is any numbers that need to be excluded from the domain. We can use any number as an input that we want except for the number 3. If 3 is an input, then we got problems. We've got division by 0, which is mathematically undefined. So the way I'm going to state my domain, I'm going to say the domain is all x such that x cannot be positive 3. So another way of saying this is any number besides 3 is allowed as an input. All right, number 15, again, it doesn't matter about the numerator. The numerator can be 0, but the denominator cannot be. So it's probably pretty obvious. You probably don't have to set each of these equal to 0 to find out what the domain is. So let's just get right to it. For the next problem, number 15, the domain will be all x such that x cannot be positive 2, and it also cannot be negative 4. Each of those numbers would create 0 in the denominator, so therefore they cannot be part of the domain. They cannot be inputs. Sometimes it's not quite so obvious. So you're always safe in just taking the denominator, just setting up your own little equation, take the denominator and make it equal to 0 and solve. So to solve for x, I would do the cube root of both sides, and the cube root of 8 is 2. So my domain, again, it's going to be all x such that x cannot be 2, because if we did plug 2 in for x, we would get 0 in the denominator. Number 21 is kind of interesting, because if I take that denominator and make it equal 0 and solve, then I get the imaginary number I. This is a pure imaginary number. Specifically, it would be plus minus 2i, the square root of negative 4. Well, since I is not real, what that tells me is there is no possible way to input a number for x and create 0 in the denominator. So a tip for you is, in solving this denominator equal to 0, if I is a result, then you're going to have all real numbers for x. There isn't a way to input a number to create 0. And so we can say x such that all reals. Okay, any questions so far? Set the denominator equal to 0 and solve. Solve for x. Okay, let's try this one. Obviously, I'm not worried about 4 being 0. I just worry about the part of the denominator that has the variable. So let's take x squared minus 9, make it equal to 0, and solve. And anytime I do the square root of both sides of an equation, I have to include plus minus. So in this case, there are two numbers that potentially, when plugged in for x, would create 0 in the denominator. So my domain is going to look like x such that x cannot be positive 3, and it also cannot be negative 3. All right, questions so far? Okay, why don't you turn in your book so you can have a reference point. Look at page 351. And we'll work through some of these examples. Just slide over with somebody. Okay, so number 25, we are given a graph, and it's our job to find out the domain and range from just looking at a graph. So looking at number 25, I'll get some help from you. Remember, domain means where does this graph travel as it relates to the x-axis? Well, it's pretty much traveling forever and ever, both left and right, except for one particular number. And what is that number? The number is 2. Okay, I think I heard somebody say that we're going forever and ever left and right except for where x equals 2. Y'all see that, the vertical asymptote? So we'll state the domain in this way. All x such that x cannot be 2. And now let's look at the range. That's looking vertically, traveling up and down. What number needs to be excluded from the range? What is preventing us from continuously going up and down along the y-axis? Okay, and for the range, that's using the y variable. So range would be y such that y cannot be 1. Okay, intercepts. We are looking for where this graph is crossing either the x or the y-axis. Do you notice that it's going through the origin? So you could basically say we have an x and a y intercept of 0. Horizontal asymptotes. You can see that's a horizontal line. It crosses the y-axis at positive 1. So that's the equation. Make sure you put horizontal asymptotes in terms of y equals some number. Vertical asymptotes should be in terms of x equals a number. In that case, it's going to be x equals 2. We haven't talked about oblique asymptotes yet. We will in just a little bit, but the word oblique just means slant. You're going to have, sometimes you have asymptotes that are lines that have a slope, either a positive or a negative. So obviously we don't have any oblique asymptotes, but just look over a couple of problems. Look at number 27. That's a picture of a graph having an oblique asymptote. See how it goes to the origin and it has a slope of, looks like positive 2. All right, so for this one we can just say not applicable. And I think we're done. And so when you get to that block of problems, this is the kind of thing you're going to be doing, looking at graphs and identifying the key characteristics of the graph. Okay, let's jump to number 27. Any thoughts? Get some help from you. Any thoughts on the domain? Where is this graph traveling, or maybe where is it not allowed to travel when you think of the x-axis? Okay, I see 0. So would you say any x except for 0? Does that sound good? All right, so for the domain we will say x such that x cannot be 0. And what about the range? Is anything preventing us from going from negative infinity to positive infinity without interruption? Well, it looks like we're passing through 0 going this way. Does it look like it's going forever and ever up and down without a break? Yeah, for the range in this case, we could say all reals. Okay, do you see any intercepts? We'll start with x-intercepts. Any x-intercepts? Okay, we're crossing the x-axis at -1 and +1. Do you see any y-intercepts? Nope. All right. Question? We're not crossing the y-axis at 0 with our 2 blue lines. Are you looking at the pink line? Yeah, that's a good thought. That pink line is actually going to be an asymptote. So, yeah, when you're looking at the graph, you're looking at the 2 blues. Okay, do you see a horizontal asymptote? Horizontal means completely running left to right. No, well, it's got a slope of 0. So it looks like there is no horizontal asymptote. There also isn't a vertical asymptote. But there is an oblique asymptote. So for oblique asymptotes will be the equation for a line. Just think y equals mx plus b. Well, what's the b? Where's this pink dotted line crossing the y-axis? Okay, so b is understood to be 0. What's the m? What's the slope of that pink dotted line? Looks like 2, right? Question? Oh, I didn't see that. Yeah, I'm glad you told me. I didn't even see those 2, the above and below the y-axis. So good catch. So yeah, we need to change our vertical asymptote. It's right on top of the y-axis, so that's x equals 0. Thank you. So what's the equation for the oblique asymptote? If we put it in y equals mx plus b, y equals 2x. Just identify the slope and the y-intercept, and remember slope-intercept form. Okay, any questions on that block of problems? How you can look at graphs and pull out this information? Okay, then I just picked one or two out of the block of problems on page 352. The directions, as you can see, are to find vertical, horizontal, and oblique asymptotes, if there are any. And you don't have to graph these. We're going to save graphing for later. So let me go through the ways that you can know if you have these. Vertical asymptotes, we'll start there. Vertical asymptotes are numbers that make the denominator equal 0. Be careful though, because if you can cancel, you need to go ahead and do all canceling first, because you may, I'm just going to give you an example. This is not number 43, completely different problem, but I just want to make sure you're aware. Maybe I have this rational function, and I just made the statement that vertical asymptotes are numbers that make the denominator 0. So right away you might be thinking, well, I have a vertical asymptote at x equals -4. Well, the fact that I can cancel means that now I do not have a vertical asymptote. Now I do have something else that's not covered in this lesson. I have what's known as a hole in the graph. But just be careful. If you can cancel, you need to make sure you do all of that first, because what looked like a vertical asymptote actually isn't, because that denominator has been removed by canceling. Well, I can't cancel here. Remember, I can cancel factors but not terms, and x down here in the denominator is a term. This x is a factor, so I can't cancel. Those are like oil and water. So I am going to have a vertical asymptote where the denominator equals 0. It's going to be the vertical line x equals -4. Remember, vertical asymptotes need to be written in vertical line equation form. X equals some number. Okay, so let's talk about the horizontal asymptote rules. And over here to the side, we've seen this in Algebra 2, but it's probably been a while, so I'm going to refresh your memory. For horizontal asymptotes, it's all about the degrees. I'm going to say it this way: compare degrees. What I mean by degrees is, if you look at a variable and look at its exponent, that's the degree of the numerator and the denominator. So the numerator has a degree of 1 because x has an exponent of 1. If this x were squared, then the numerator would have a degree of 2. You just take the largest exponent of a variable, and that's the degree. A constant with no variable has a degree of 0. Okay, so when I compare the degrees, 3 things are possible. I'm going to say it like this. If the numerator degree is greater than the denominator degree, so I'll just illustrate, don't change your problem, but I'm talking about this situation. The degree of the top is 2 and the degree of the bottom is 1. If this happens, then you do not have a horizontal asymptote. Just take a look at the degrees and compare them. Okay, our situation is where they're the same. The degree of the top is 1 and the degree of the bottom is 1. Well, this one's a little tricky, but it's not bad. When this is your situation, the degrees are the same, you are going to have a horizontal asymptote, and the number is made up of these lead coefficients. Just think of a fraction that you're going to make. In this case, it would be 3 over 1. And so I put that together. I'm going to have the line y equals 3, which is going to be my answer. So degrees are the same. Just look at the lead coefficients and put the top coefficient over the bottom and simplify if necessary. I think I'll just do a general statement here. I'm going to call this A over B. A is the lead coefficient, B is the lead coefficient on the bottom. Well, the only other possibility is that the numerator degree is less. That doesn't happen here, but it certainly might. If the numerator degree is less, for example, maybe this were x squared on the bottom and it's still x to the first on the top, then it's always the same horizontal line. It's the line y equals 0. And that's just another way of saying the x-axis. Okay, so look at the degrees and run through this little list, and that should guide you toward horizontal asymptotes. For oblique asymptotes, we don't have one here, but here's how you'll know if you do. Oblique asymptotes will have the numerator degree is 1 more than the denominator. I think on our next problem we have one. And I'll show you how to find it. Have we done long division with polynomials in here? Okay, so we need to go through some long division. Okay, so we're finished with this problem. We've identified a vertical asymptote, a horizontal, and there is no oblique. All right, so let's take care of this problem. First of all, if factoring is possible, you should do factoring especially in the denominator, but I would say really both. If you can factor, do that first. What we have here is the difference between two cubes, and that also factors. Do y'all remember how to do that? Remember this? No? Well, the difference between two cubes, recognizing it first. First of all, you do the cube roots, and then we're going to make a trinomial like this. Square the first one, multiply them together, and then square the last one. If this were the sum of two cubes, it would be the same way, except this would be plus and this would be minus. But I'm doing this so that you can see how we're able to cancel. Okay, so looking at this, what is my vertical asymptote? Because remember, I'm able to do this. Well, it was that, but since I'm able to cancel, now I just have 1. It's going to be x equals 3. Do I have a horizontal asymptote? Look back on your previous slide. How come? I see some people say no. Why do we not have a horizontal? The numerator degree is greater than the denominator degree. Okay, do I have an oblique? I do, because the numerator degree is 1 more than the denominator degree. Okay? So here's how you find oblique asymptotes. We need to do a little lesson on long division with polynomials. So if you have an oblique asymptote, this is how you find it. I'm going to divide the denominator into the numerator. And since I'm going from x to the third all the way down to a constant, I'm going to just fill in some spacers. I'm missing a squared term and I'm missing a linear term. Oh, and that should be minus 8, and I put plus 8. Long division with polynomials is really pretty easy. You really just divide the first term into the first term. That's really the only division that takes place. So if I divide x squared into x cubed, it goes how many times? Just think x cubed divided by x squared and simplify. Isn't that just x to the first? Subtract the exponents. So I'm going to, since it's x to the first, I'm just going to put it over the x to the first term. It's just a match. Now, just like in typical long division, let me go back to the good old days with just regular number long division. When I knew 3 goes into 28, how many times? And what did I do with the 9? When I multiplied times the 3 and I put 27, remember that? Well, same thing happens here. I'm going to multiply x, but it's going to be distributed to all of these. Okay, so what's x times x squared? And x times negative 5x. And x times 6. And just like in typical long division, I'll go back to my real number example. What did I do here? After I multiplied 9 times 3, what did I do with the 27? Subtract, okay? And that's what I do in polynomial long division. Well, the x cubes are going to cancel, and then 0 minus negative 5 is positive 5x squared. And 0 minus 6 is negative 6x. Okay? Now I do the same thing. First term into first term. How many times does x squared go into 5x squared? 5 times, and it's positive. 5x squared minus 25x minus 30. Okay, the x squares cancel. Negative 6 plus 25 is 19x. Forgot to bring down the negative 8. Negative 8 minus negative 30. Negative 8 plus 30 is 22. Now at this point, in regular long division, we would keep going and show a remainder. But for your oblique asymptote, you just have to go until you can't divide any longer. X squared is bigger than x. I can't divide x squared into x because it's bigger. So I'm finished, and this represents a line. This is going to be my oblique asymptote. It's the line y equals x plus 5. And so we're done. Okay, questions on long division, oblique asymptotes? That's a new concept. All right, let's try this one. Let's factor everything first. In the numerator, I've got the difference between two squares. So hopefully you remember how that factoring looks. In the denominator, I've got a GCF. Can I factor any more? Numerator or denominator? Look closely. Any more factoring opportunities? Look at the numerator. What's in the numerator? Yeah, that's the difference between two squares also. So let's factor a little bit more. The factoring really makes these quite a bit easier to deal with. Okay, now cancel if you can. And we have some matching factors that we can cancel, the x minus 1s. Now let's focus on vertical asymptotes. Now that we've canceled, look at the variable that didn't cancel and what would make the denominator 0 if we put a number in for that variable. Okay, so we're going to have a vertical asymptote at x equals 0. Do we have a horizontal asymptote? We don't, because the degree of the numerator is bigger than the degree of the denominator. Do we have an oblique asymptote? We don't, because the degree has to be only 1 more. Okay, this degree is 2 more than the denominator, so we will, however, this will be a future lesson, we will have a hole because we were able to cancel. And I'll just preview it. We have a hole at x equals 1. But you're not looking for holes in this exercise. We'll save that for later. Any questions? Think you're ready to practice some?